So in section 11.2, we've discussed in 11.1 that a vector is a journey, gives you a distance to go and a direction to go in. If you start the journey in a different place, you'll end up in a different place, but that's fine as long as you follow the same instructions. So instead of thinking of it as a direction and a magnitude, we're going to think, well, how are we going to notate that? If we want to start here and finish here, I could tell you the direction and the magnitude fairly directly, because I could tell you, well, go at this angle and go for this many units. And in other areas of maths, when we start looking at polar coordinates, that is in fact how we'll start thinking about things. But the more usual way, the sort of Cartesian way, the way like on an XY set of axes that we can use, is to say, well, in this case, let's look at how far across you've gone and how far up and down you've gone. And this is, we're familiar with this since before GCSE, so I won't labour the point. This vector A might be 3, 4, because we've gone 3 across and 4 up. That's what it would mean to have a vector 3, 4. The top number tells you left and right, positive for right, negative for left. Bottom number tells you up and down, positive for up, negative for down. Okay, so this is what we call a column vector. We can call this the horizontal component, or if you like the X component, this is the vertical component, or if you like the Y component. If I take it and I multiply it by a vector, by a scalar, that would be 3 times P, 3 times Q. Because if I made that 3 times as long, vector A, vector A, vector A. So that whole thing is 3 lots of vector A. I've gone across, across, across. I've gone across 3 times as far, and I've gone up. So that would be P, P and P, Q, Q and Q. So I've gone across 3 lots of P and up 3 lots of Q. So we're not just saying, well, if we're timesing by a 3, we'll probably just times both things by a 3. We're checking that it fits with our idea of what vector, timesing a vector by a scalar is, okay? We usually use a Greek letter. If we're going to times by a scalar, scalars are often used, we often use a Greek letter to represent the scalar. So here are some Greek letters that you might have met before. Lambda is this one, mu is this one. So I can say lambda times PQ equals lambda times P, lambda times Q. That doesn't mean anything other than, if I said A times the vector PQ is equal to A times P, A times Q. Okay, it's just that it's sometimes helpful when we've got some objects that are vectors, some objects that are scalars. We tend to stick to the usual letters that we're used to for the vectors, make them bold or underlined. And then if we do have a scalar, just to make sure that we're not getting them confused, if our underlining gets forgotten or if our bold font isn't sort of obvious, then we make it a Greek letter as well, just to sort of remind us. If we're adding together column vectors, vector A plus vector B, well, how far have I gone across in vector A plus B? Well, I've gone as far across as I needed to for A and as far across as I needed to for B. So if I've got 2 vectors, PQ and RS, and I'm adding them together, then the total horizontal component is the horizontal component of the first one plus the horizontal component of the second one. And then vertically, I've gone up as far as A and then up as far as B. Okay, so that is Q plus S. So again, we do this one component at a time, component-wise we call it, first components, then the second components, but we do that because it fits with our idea of vector addition that we've already described in section 11.1. The alternative notation for this is the I's and J's notation, which you may have met already. Depending on the order that you're doing this course and what courses else you're doing, you may not have met this, but it works like this. Vector I is this vector, 1, 0, and vector J is this vector, 0, 1. Okay, so if I pick any old vector, let's say -3, 7, well, I could write that as -3, 0 plus 0, 7. And I could write that as -3 times 1, 0, and 7 times 0, 1. In other words, -3 times I plus 7 times J. Okay? So these notations aren't actually separate notations. It's just that I is this specific vector, J is this specific vector. And if you think about it, if you were processing this, it's going to be a lot easier to have I's and J's in bold type than it is to make sure you've got the columns all the time. And other people just prefer the I's and J's because they look like algebra, all on one nice neat straight line with 2 variables I and J, rather than introducing this new idea of a column vector. Excuse me. So In general, if you've got a vector PQ, that's the same as P lots of I plus Q lots of J. It's pretty straightforward to switch between the two, the I and J notation and the column vector notation. Now, my advice to you is, in pure maths, it's a little bit more usual to use the column vectors. In mechanics, it's a little bit more usual to use the I and J notation. Pick the one that you like. If you like the I and J notation, fine, go for that. If you like the column vectors, fine, go for that. When you get a question, it doesn't matter if it's mechanics or pure, translate the question into the notation that you like, and then at the end of the question, make sure you've got the answer in the notation they give you. So if they give you a question with I's and J's, then at the end of it, put your answer in I's and J's. If they give you a question with column vectors, at the end of it, put your answer in column vectors. Just looks a little bit neater like that. If you forget, they probably won't knock marks off. If you really like column vector notation, I like column vector notation, I only use I's and J's when I'm kind of forced to, go for column vectors all the time. If you like I's and J's, stick with I's and J's all the time. Okay, there's not many situations where you're going to have to use one particular notation rather than the other. As long as you're aware of both, you can interpret both. And if you're really forced to, you can use the one that you don't like, and that'll be fine. The rest of the time, stick with the one with the notation that you like. Okay. Example 7 is some fairly straightforward bits, but let's just have a quick look. If A is 3i minus 4j, what's half A? Well, if it was a column vector, we'd half both of the components. So in this case, we're just going to half both of the coefficients. So we half the 3 and we half the minus 4. Okay. A plus B. Well, if this is A and this is B, we're going to add together the i's and add together the j's. So we can collect them like collecting like terms. Okay. So 3i plus 2i would make 5i, minus 4j plus 7j would make a total of 3j. Okay, and then we get more and more complicated versions of that. They build up through the examples. I'm not going to labour the point too much. I'll leave you to work through those separate examples and check that you get the idea, swapping between the two notations. It's worth, at some point, if you haven't met this before, do go through those examples, read them carefully and think to yourself, right, this is in IJ notation, how would it work in column notation? How would this question work if I didn't think of it as I's and J's, if I thought about column vectors, would it change it? And just make sure it's all sort of straight in your head. That's for the examples and the questions in 11b as well. And once you're used to it, you'll realise there's really very little to swapping between the two. Okay, end of section 11.2.